DA, specifically linear discriminant analysis or LDA, is used for dimension or feature reduction of data. This means that this is used as a pre-processing step in machine learning, and this also finds its application in pattern classification. Isn't it great that the same DA can be used for the both purposes? Discriminant analysis finds its application in finance, for example, approval of bank loan application, in marketing, for predicting customer trends, in medical science, for example, image recognition, etc. It is a state-of-the-art business approach that can drive successful strategies and can propel decision-making processes to greater heights. Data scientists and business analysts can use this tool and use its result to compose new processes and design that may be beneficial for the organization. This video demonstrates and helps us to get information about the application of DA and the core mathematics behind it, which will help us to design problems and apply DA to solve the problems existing in corporates and various industries. So if you feel the need to dig deeper and know more about it, sit tight as we are going to bring you all the information that you need right on your screens. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments. So very quickly, let me walk you through the agenda for today's course. In today's course, we are going to understand discriminant analysis concept in detail, and then we will do an exercise on the application of Fisher's discriminant analysis.
We are assuming normal distribution, multivariate normal. I'm just saying this is on group 1. The group 2, let's say group 1 is defaulter or something, group 2 is this. Now the separation is not good. In other words, I am not able to differentiate. The overlapping cannot be made equal to 0 in segmentation. There are always undecided people. Supposing I take another example here. This is my G1. This is my G2. Now, this is discriminating, differentiating better than this. So, how to achieve the largest separation possible between the two groups? Now, what is your support vector machine saying? I have generated a number of hyperplanes. Using the best hyperplane, can I achieve the largest separation between the classes? In a way, support vector machine also does that, but the algorithm, kernel, the other methods are completely different. But the largest separation which I want to achieve between the classes is the aim of support vector machine as well as discriminant, even though both are entirely different in their approach and other things. But this part, as a classifier, if you take support vector machine, you can also use support vector for regression. As a classifier, if I use, the largest separation can I achieve between the classes is the aim of support vector machine, which was the aim of Fisher in 1936 when he wrote that immortal classic paper in taxonomy called Fisher's linear discriminant analysis. The objective is to, so the key word which you have to remember is, when I do an exercise, can I achieve the largest separation between segments? Market segmentation. How to achieve this largest separation? That means what are the clusters which you do initially and then separate the clusters. So it is a supervised learning, but I can't do a supervised learning unless I know the clusters. So I do a clustering using an algorithm. K-means are hierarchical. And then once I form the cluster, I do some profiling. The profiling tells me these are the 3 clusters: low risk, medium risk, high risk clusters. Then can these characteristics which I apply for a clustering sharply differentiate these 3, low risk, medium risk, high risk? Can I use discrimination or a support vector machine? So that, and then a classifier. That's how the journey, an unsupervised journey will lead to a supervised journey ultimately. Supervised journey means I am using models to predict. There is a fundamental difference between explanatory model and predictive models. While all predictive models need to be tested for explanatory power, but they do not stop with explanatory alone, they predict the outcome for new records. So in a predictive model exercise, typically you develop the data into training and testing and then find out whether the model works for the test. That is the hallmark of predictive analytics. But you need to test the explanatory power, whether the model works, and that is where these models are very powerful. So three aims are there: profiling, differentiation, classification. These are the three aims: profiling, differentiation, classification. Now profiling, why I say, because I have three clusters I may profile, what they are, what are the characteristics, or I have predetermined the three groups. My company itself knows these are low risk people, medium risk, high risk. Can I profile them to find out which characteristics actually differentiate them? Profiling. If so, can I use some visuals, descriptive measures? If so, can I differentiate them using a discriminant? If so, can I classify them? So these are classifiers. This is how you can, even in logistics, you classify ultimately. So these are classifiers. Support vector machine classifier, neural network classifier. Each one of them has its own merits and demerits. We have to select that. But the three goals in the analytics world, they are extremely critical. In your capstone, anything you do, you have to understand this profiling, differentiation, classification. Sometimes you use the word discriminating. They are discriminating against me. That's also discrimination. What do you mean? You are separating somebody or achieving something. But here, the market segments. So, how this is a scoring model? Let me just start an exercise and explain the philosophy of Fisher, what he has done with the classroom exercise, which I will do with you in Excel solver. Walk the talk. Completely, I will do A to Z. You have to listen to me and you have to do that. And I hope the solver clicks. You don't make a mistake or something. Very slow I will go and all of us should get the same results. So we'll do that. And then I will show you R and all those things. Let me explain this. There is a classic problem given in one of the very good books written by Winston and Albright, Management Science Modeling. From that book, I picked up this example of 24 records only to explain what is discriminant analysis. And this exercise that is given is solved by some genetic algorithm in the book, where the solution can be multiple in nature. It's difficult to precisely say which one is the best, but I have applied the orthodox, traditional, the voice of Fisher. Today Fisher is no more, but the voice of Fisher we will do in this exercise and understand what is discriminant analysis. So, financial ratio file, the file contains 24 records, 24 companies are there, and the two variables that are there, EBITDAs, earnings before income and taxes divided by total assets, ROTC, return on total capital employed, and group 1, the most admired, group 2, the least admired. Most admired is 1, least admired is 0. I can apply a logit also. But most admired, least admired. And I have taken equal sample size, 12, 12, to avoid controversy. Sometimes you do not get it in life. It will be so unequal. One will be balancing only 10%, one group, another group 90%. That we have to deal with that anyway. But this is the exercise. So, the most admired and the least admired. Apply linear discriminant analysis to classify a company as most admired or least admired. Which variable appears to be most important for this classification? The relative importance of the attributes, quantifying the relative importance in a landing page, in a web page, what are the drivers that are relatively important for maximizing the click-through rate in a landing page? If you say, what are the things, which one is more important, less important, how do I understand? These two questions are there. And let us now open the Excel file and just see here what it contains. I have made it 1 and 2, most admired, least admired. Group 1 for most admired, 2 for least admired. Instead of 0, 1, it is 1, 2. It does not mean 2 is bigger than 1. I have put 1, 2. Okay. Sir, in class file, this is in class exercise which I want to do. Classifier, Z score. I am going to build a model on how Fisher would have imagined, would have done that. And let me just erase the board and write some basic things for you. Then I will discuss the Altman's paper also with you to reinforce the concepts. Now Fisher, what he wrote was, in this case, is an Z score. It's a scoring. Z equal to, let's say, A1 x1 plus A2 x2. Where A1 and A2 are the discriminant weights. A1 and A2 are the discriminant weights. I will develop discriminant as per Fisher without the constant. The constant is the cutoff point score. So I do not want to complicate. A1 x1 plus A2 x2. Just like a regression equation, Z is a score actually. Because 1 means most admired, 2 means least admired. So it is a classifier. Y is a function of this, but it's not this. Therefore, I am developing this score. X1 represents the ratio, for example, EBITDAs, the column 1. X2 represents ROTC. Mathematically, it is easy for me to put X1 and X2. That is why I am not putting it. So, X1 is the EBITDAs ratio, earnings before interest and tax divided by total assets. X2 is return on total capital employed, ROTC. What are A1 and A2? I do not know. I have to find out. If I know that, I can find out the score for every 24 records. Once I know A1 and A2, I will plug in the values of X1 and X2. These are all there. I will shamelessly do it with a calculator, with an Excel. Very easy. But what are A1 and A2? So Fisher, what he is saying is that I have two groups. Therefore, if I compute Z1 is equal to the mean of X1 and X2 for group 1. The mean of X1 and X2 for group 1. A1 times, what is the mean? X1 bar. But I will do it for the first most admired one. So I put with your permission within bracket 1i, meaning it's group 1, plus A2 times X2 bar, and within brackets I put it is group 2. Is it okay? Sorry, not group 1. This is X2 is also for group 1. First I will have to do group 1. One is admired. So let me put, to have clarity, let me put here as the canonical thing. 1 means this. I will put here 1 and 1. This is group 1 within brackets. I am not making it a subscript. Within brackets I am writing this. Meaning I compute the mean for the first group. The Z score is the score which is at the centroid. I am just taking the mean score. Then Z2 will be A1 times X1 bar group 2 plus A2 times x2 bar group 2. Am I right? Now Fisher says the group centroid, this is the score Z1, which I apply the mean, which I can calculate in Excel. Now, can I separate these Z1 and Z2 by the largest distance possible? By the largest distance possible. In other words, Z1, Z2 may be positive or negative. So, Z1 minus Z2 equal to A1 times x1 bar 1 minus x1 bar 2, isn't it? Plus A2 times x2 bar, correct? x2 bar group 1 minus x2 bar group 2. This is what it will happen when I open the bracket and subtract it. Now the distance between the two must be the largest. That means this must be the largest. What I have got must be the largest. But then I have a problem. I'll have to take the absolute value of the distance, because the distance can be negative. Am I right? The distance can be negative. But what Fisher does is, he is saying distance square. Square it. This is between sum of squares in the ANOVA. Between the groups, A1 times this plus A2 times this, the whole square, is the between sum of squares, which is the distance square. If I maximize distance square, I am maximizing the distance. So, the largest separation possible. While doing the largest separation possible, there could be differences because of the variance of the two groups need not be identical. In other words, the clustering algorithm also says homogeneity in a cluster, heterogeneity between clusters. And therefore, what he says is, if I have to maximize this, I will have to control the variance within each group. If the variance can be plus or minus, it will do. So, what he assumes is, the two group variances, I am pooling them. So, let me write, this is my numerator. Let me write here numerator, which is between sum of squares. Now, denominator, what he says is the variance of both the groups. So, let me write here, the denominator is a variance of Z. Let me call it variance of Z. If the variance of Z is equal to 1, what he is assuming is maximize numerator by denominator, where numerator is between sum of square, denominator is within sum of square. This expression you maximize. Max of this expression is required. Max of this expression is required. The numerator is between sum of squares. The denominator is within sum of squares, which is a famous F ratio in the ANOVA. I hope you would recall. Between the groups, within the groups. Now, why he is doing that is, if the denominator is minimum, numerator by denominator has to be maximized. That means I will set the denominator equal to 1. I will set the denominator equal to 1 so that I am maximizing this expression. Maximize this expression subject to the constraint denominator is equal to 1. And this is called the Mahalanobis D squared. D squared equal to Z1 minus Z2 whole squared. Okay? This is the mean I am taking, divided by the variance of Z. Maximize this Mahalanobis, this D squared, you set the denominator variance of Z is equal to 1. This is what Fisher has done. Then the values of A1 and A2 are found, which will maximize this expression between the groups sum of square to within the sum of squares. By a non-linear optimization, I can find out the value of A1 and A2. In other words, I am just making this part extremely simple for you. In this particular case, there are 2 variables. I can have 20 variables, doesn't matter. The analogy will work. All I am saying is there is a numerator which separates the 2 clusters or the groups by the largest distance, and that I have found out. But when I do that, it could be negative. So when I want to maximize, I'll have to maximize the absolute distance, which is same as distance square. Then divided by the variability within the group, which is the homogeneity to be assured. So therefore, this ratio will have to be maximum for group separation. Subject to the constraint, the denominator variance of Z is set equal to 1. This is exactly what Fisher has done, and he has done it by hand in those days. Calculus and all that, Lagrangian multiplier, calculus and all that, 1936. So, we will apply this, find out the value of A1, A2, then say how to classify. That's the exercise we are doing. Now, only one request I will make. What is the denominator variance of Z? I have not answered. I have not answered. What is the denominator variance of Z? What is the variance of this expression? Go back to statistics. These 2 are random variables, x1 and x2, and we need not assume they are independent. They may not be independent. There may be a covariance term. Right? Actually, this is equal to, let me write it here on the top. Variance of Z equal to A1 square times variance of x1 plus A2 square times variance of x2 plus 2A1 A2 covariance x1 x2. And mind you, these are sample covariances, so the denominator has to be divided by n minus 1. How do you remember this? Very simple. A plus b whole squared, you remember. A squared plus 2ab plus b squared. A squared, a1 squared, variance of x1, plus a2 squared, variance of x2. 2a1, a2, covariance x1, x2. Suppose I have x1, x2, x3, what will you do? a1 squared, variance of x1, a2 squared, variance of x2, a3 square variance of x3, 2a1 a2 covariance x1 x2, 2a1 a3 covariance x1 x3, 2a2 a3 covariance x2 x3. Like a child you can write. What is there? Let it be 20. You can write still, or use a matrix. But this is a concept. I am not assuming x1 and x2 are independent. This is another beauty here. It's actually a quadratic expression. The denominator is quadratic. The function is called linear discriminant because this equation is linear. But the values of A1 and A2 are obtained by non-linear programming, which you are doing now. You are doing some optimization and all. I am going to make use of that. We have already done it in logistic, but here it is even more interesting. So, we need to find out the values of A1 and A2. Now, mind you, this variance of Z is a general expression. This will exist for the first 12 observations. In other words, there is one variance of Z for the first group, one variance of Z for the second group. So, what is the pooled variance of Z? The average of the two. This is a general expression, but this will hold for the most admired one variance, least admired another variance. Since the sample size in this case is equal, I will take the average of the two. The weighted average method, I know you have done a t-test. Have you not done a t-test? How do you compute the pooled variance sum of square S squared? N1 minus 1 S1 squared plus N2 minus 1 S2 squared divided by N1 plus N2 minus 2, which follows a t distribution with N1 plus N2 minus 2 degrees of freedom. You have forgotten. Why do you multiply by N1 minus 1? It is because the sample variance has a denominator N minus 1. Only the population has a variance n denominator. And here I don't have to do it. Why? n minus 1 in this first group is 11. 11 into variance of the first group plus 11 into variance of the second group divided by 22. Anyway, it will be half because the sample size are equal. So, all I am going to ask you, a very simple thing, you will have to cooperate. Find out the variance of the two groups in Excel. Simply take the arithmetic mean of the two. You know the denominator, you know the numerator. Then just like that, the results will follow. And Fisher's discriminant analysis, as Fisher has done, is what we are doing now. That's the starting point. So, let me start with this introduction. The board expressions are required. I will just create something with you and all of us should do, and then make sure everybody in the class must say, I have understood. First step, how to get the Z score, Z value, then classification I will tell you. That's the first step, okay? So, let me create something here, a little, and maybe A1. Let me put a font size here also. Shuma, let me be generous, 16. Let me start here. A1, A2. W1, W2 if you want you can put, doesn't matter, but fish, I am just using some symbol. With your permission, I am setting initial values for this 1 and 1, okay, and color it with your permission. These are the unknown cells, okay. Now everyone will tally with me because you have to only enter the numbers now, A1, A2. Am I correct? Then I put here x1 and x2 is this. If you want, we can in bracket, I can put this as x1. Do you want that way? So that you do not blame me. I put that. Or the better way would be A1 into this, I'll have to multiply. So, if I put here group 1, group 2, let me see here. 1 minute. Let me see whether that other one helps me. Transpose. Here, let me put here group 1, group 2. Difference, eh? So let's write that. Okay, let me, the previous one was correct, somehow I made it, doesn't matter. If I had done that, then I can directly use some product, right? Because A1, A2, A1 into the means difference, A2 into the difference will be automatic, it doesn't matter. Now, is equal to means, is equal to average of the first 12, 0.1913 something is coming. Are you getting it? Let us do that. Difference I will come later. First, let me complete this. Group 1, are you getting this 0.9133? Then for group 2 is equal to average from 13 onwards. I will have to put what I am getting. This is coming. Now let us do the ROTC also like that, is equal to average ROTC is equal to average Now I put here difference here. The group centroid difference is equal to, in this case it is positive but doesn't matter, it can be negative. In all cases it need not be positive, it can be negative, is equal to this minus this, even a child knows, why not you, is equal to this minus this. You agree with me, sir? So now, what is the equation saying there, numerator? Z1 minus Z2 whole squared is A1 times the difference in the mean, this part is the difference in the mean, A1 times the difference in the mean plus A2 times the difference in the mean of the two groups, the whole expression whole squared. It is not this square plus this square, that is wrong. It is the entire expression whole squared, like your a square plus b square plus 2ab, and therefore what we do here with your permission is a1 times I will have to multiply this, a2 times I will have to multiply this, some product, isn't it, is equal to, so the numerator part, let me write here with your permission, numerator, let me put here, numerator. What is the numerator? Is equal to some product, comma, this, and with your permission I should open an outer bracket also here because I have to square this. Let me explain this to you. Some product will give me that expression, but I have to square it, Z1 minus Z2 whole squared. Therefore, I put another outer bracket, cap 2. Am I correct? One more bracket I put here, outer bracket, cap 2. That is the total, the overall scheme of things, 0.137 something you are getting? Okay, whatever. Is it okay? sum product, let me show you this here so that you can correctly see. Is equal to sum product, okay, is equal to sum product K2 L2 O4 P4, the whole square, I put an outer bracket. Is it clear to you? In other words, in Excel, I am not doing anything special. This part, outer bracket is sum product. Then I put a bracket square, the sum of squares. You should not by mistake square only the first two terms, that is incorrect. The whole expression is the distance and that is a square. Are you getting it? Getting the point? Sum product, what I mean by that is, let me explain this to you here. A1 into this plus A2 into this, whatever I get, that has to be squared. So this is what I am saying, I am doing here. A1 into the difference, this stands for the difference 1, plus A2 into difference 2. This is one difference in the group, means this is another difference. Everyone in the class, if you have a doubt, I will clarify now, it's very important. Square. Some angularity you should have to see this here. It is difficult, I know, you are sitting there, the board cannot be rotated now. A1 into the difference, yeah, this is one difference, hello, the difference represents the group mean difference for the first variable, the difference, A2 into the difference for the second mean difference. This whole expression is to be squared, and that formula I have just put, and then this, if I double click, this is exactly the formula. Are you getting this? Initial values. So this is my numerator. Now let me put here, with your permission, A1 square, A2 square, 2A1 A2. Do you have any objection? I am writing it A1 square, A2 square, 2A1 A2. I am going to calculate the variance. So I write this here. Okay. Hello. Now what is A1 square? Is equal to this square. I will have to square this. If you simply write 1, it will not come. Then A2 square. What is my A2 square? Is equal to square, the second one. Because everything must be a formula for Excel to understand. Sometimes people write 1, 2 and then they're not getting, I'm not getting the answer, so I'm avoiding. I am forestalling objection. I know the trap, so I'm just saying that. What is 2A1 A2 is equal to 2 star A1 star A2. 2A1 A2. So this is a multiplier I am going to use for calculating the variance and covariance. So, but this is a multiplier. So the first one which I am going to do here is variance group 1. Ladies and gentlemen, variance group 1. This expression I am going to do for group 1 and group 2, then pool that as a weighted average. In this case, it is simple average only, they are equal sample size. Okay? Somebody? Yes, some of you. Am I making it clear? So now, how do I do that? Now, in Excel is equal to variance of x1 I want for the first group. is equal to variance is not for the population, it is sample variance dot S. Kadak. You put that for the first group only. Then variance x2 is equal to var dot S for the second variable. Tak. Then covariance I need is equal to covariance dot S. Some old system 97, then it's only one covariance will come, they will not get the correct answer. I have to forestall objection now. Covariance dot S is available in the current Excel. Some very old version, if you are using something like 2007 or 3 or something, in which case what you have to do is, you will have to find out the variance, cross product variance, then multiply by n whatever is there, then divide it by n minus 1, because the previous one did not have. Covariance dot S. In other words, you will have to get the sigma x1 minus x1 bar into y1 minus y1 bar, you will have to multiply and then divide. But the covariance given in the previous version is incorrect, because it doesn't give for the sample. So if you have got that, then you should not say, no, I am not getting the answer, so I am just preempting. Covariance dot S is the correct one. Covariance dot S, if I do here, covariance dot S, I know you are all Silicon Valley people, you must be having 2017 Excel. Let's not have 1942 Excel and then create a problem. But even then we can do a basic principle. Comma, these two, x1, x2, point not, 1, 1, 1, 1, are you getting? Hello. Now let's do the same thing shamelessly for variance G2. For the group 2, what will you do? Is equal to variance dot S of these variables from group 13 to 24. Hello? 13 to 24. Am I correct? 13 to 24. This will be the answer. Then is equal to variance dot S. The second one, 13 to 24, I should do. Point not 46951. Then covariance is equal to covariance dot S. I should do the first one, 13 to 24, comma 13 to 24 of the second one. Once I do that, I get this expression. Am I right? Now I have to calculate. This is without the coefficients. Are you with me? This is without the coefficients. So what is my overall variance, if I have to say? Sum product of the first one plus the sum product of the second one divided by 2. Am I correct? So let me put here pooled variance. Pooled variance is equal to sum product A1 square to A2. I have to lock it because the coefficient has to be same. I have to lock A1 square, A2 square, 2A1, A2. That will be same for both. I lock it, comma, this one, plus sum product so I don't have to lock it, I can do it again, doesn't matter. Sum product I don't have to lock it. I could have copied the formula, then it would have been all right. Okay, let me see that. Okay, is equal to, let me do that, is equal to some product. Let's not lock it because we are going to multiply. I thought I should lock it here. Let me put here comma this one plus some product. I need not lock it because I am going to use this again, comma the second one. Now this part I will have to average out. I don't have to do a weighted average. Why? Because the sample sizes are equal. With your permission, I divide it by 2. Do you have any objection? The sum product of the two expressions, this plus this divided by 2. I put an outer bracket. Do you have it? I cannot do it by 2. If I have an unequal sample size, I should take the weighted average of n1 minus 1 and n2 minus 1, then divided by n1 plus n2 minus 2. That everybody knows. Okay. So this will be the denominator. What is that I am getting, sir? Are you getting this? 0.0009 something? This is my denominator. So denominator is equal to this formula, pooled variance. Am I correct? This is my denominator. Hello. The denominator I am not copying it. I am copying it as a formula here. The denominator, let me double check, n10 I am copying it there. Do you have any objection? So this is my denominator. Now goal. What is my goal? Is to maximize, no doubt, is equal to numerator by denominator. Numerator by denominator. 14.744, are you getting? This is the goal. We have to maximize by varying the cells. This is the goal. We have to maximize this by varying the cells A1 and A2. You get the answer. The discriminant coefficients of Fisher, the first step. And therefore now, ladies and gentlemen, and we have to set the denominator equal to 1 as a constraint. So data solver, we take, what is the objective? This cell, maximize the goal. What are the changing cells? These two, yellow color. This is the changing cells. What is the constraint? Add a constraint. The denominator which you have got there equal to 1 you put here. Click OK. Now, hello, can I do it again? Okay, reset all. I will be slower than the Shankota passenger. Very, very slow to satisfy you. Hello. Objective. Okay. Objective. I can walk there, but the system is here. If there is another system, I can walk and do it there also. I wish some days they put the table there also, so that it is equal. First next hour we can put there. It's not possible. Computer action is here. What is the objective? The objective is, hello, the goal is the numerator by denominator is the d squared Mahal-Love base. Maximize this. Maximize by changing cells. A1 and A2 are the initial values, change them. Then a constraint. What is the constraint? Denominator is equal to 1. Don't try less than or equal to. Less than sometimes fails. Don't be adventurous. Follow Fisher. You are wiser by following Fisher. Okay, is equal to 1. Is equal to 1 is a Lagrangian multiplier. Now click OK, and then it is like a regression scoring equation. There is no hard and fast rule A1 and A2 have to be positive. It can be negative. In a linear programming problem, non-negativity constraints, you would have put there the decision variables, formulate the objective function, identify the decision variable, step number 1, formulate the objective function in terms of the decision variable, step number 2, formulate the constraints, inequality, equality, everything in terms of the decision variables, and add, superimpose the non-negativity, all decision variables greater than or equal to 0, the classic linear programming or non-linear programming. Here, these are coefficients like the regression slopes, they can be negative. And therefore, remove this unconstrained variable non-negative part, you remove it. Logistic also we have done that, do you recollect? And then GRG non-linear is correct. It is generalized reduced gradient method of a non-linear optimization, and therefore GRG non-linear because it is a ratio of 2 sum of squares. And then be generous, options you go, use automatic scale, remove it, and put another couple of zeros if you want. Integer optimality, remove it, make it 0. And GRG non-linear precision, put some more zeros, you have nothing to lose. Require bounds on variables, remove it. It doesn't require bounds on variables. Bounds will come for evolutionary solver, genetic algorithm. There is an evolutionary solver here. Requires bounds, you remove it. Okay, have you removed it? All of you? Okay, solve. Time, let's come now. You will have to do it with me exactly like that, and you would not have 4 decimal places. Those who have not got the answer, some errors may be there. How many are there? Let me try to find out. That's why I said do it with me completely, because this happens every time, everywhere I go, 2-3 people not getting. We can solve that. That's not a problem. Simple mistakes you might have made. Check all these formulas. Denominator is almost 1.00000004. Suppose you put some more zeros, it will come. If you want, I can do that for you. Solver and options, you go. The formula. See, first of all, hello, check that A1 squared, A2 squared, A3 squared, that part, have you put a actual formula cell or simply written 112? Then it will not come. There is one possibility. This A1 squared, A2 squared, A3 squared, if I have not entered the formula and simply written 112, it could be incorrect. It's incorrect. You will have to write this cell is equal to the square of this cell. Have you done that? There is one problem in solver which I want to highlight. Whenever you are doing in solver, suppose you make some mistake somewhere, A1, A2, 1 formula, or you by mistake you put that again as 1. What happens is it keeps something in the memory and keeps on giving you a wrong answer. It's possible. In which case what you should do is, you will have to do it afresh, change the registry, everything. Next time open the solver, create a new worksheet and do it, you will get the answer. That's the only answer I can give you, because otherwise it doesn't get solved. 3 cases I have resolved the crisis. They have taken the denominator and copied it there directly without a formula as a value. Then computer will not understand that. So that is sorted out. Be rectified. In the memory, it keeps some wrong answer. Initially maybe you are not checked the box. Then you have checked it. Hello? It's possible. Initially, some people have forgotten, check the box, you are not unchecked. Later if you unchecked, it keeps something working in the earlier part. So all you do is, you close it and all the later, you create a separate sheet, worksheet, and the formula, I am sure it will come, and this answer is correct. I can show you that if you do it in R also, you will get this same answer. Okay, I will show you in R. This answer is correct. So let us now Few people have some small difficulties. I appeal to you, we will correct them. Okay. There also the formula, everything is correct, but something the computer keeps, as a result they are not getting the right answer. But most of you would have got this. Now let me explain this. In the next exercise you will be victorious when you do that, and there's not to worry about it. But when we make one mistake, it takes like that. Okay. Now, the first step is, let me explain this to you. The first step is how to get A1 and A2 by maximizing between sum of square to within sum of square. This is called the Mahalanobis D square. It's a famous distance measure. Maximize between to within. You have got that now. Most of you got the answer. There are some differences. We will settle it. Even those people, their formula, everything is correct. Somewhere, some software bug. So we will resolve it. So don't be disheartened. There were 3-4 people in Hyderabad also it happened. Next day they smiled. So don't worry. You will be all right. Okay. Now I have starting this exercise. I can compute for all the 24 observation a discriminant score. Why? Because I have established Z is equal to A1x1 plus A2x2. Do you agree with that? So all I need to do here is A1 and A2 I must lock because they are same for all the 24. So is equal to some product lock it $K$2 $L2 $L2 comma the first record tack the first discriminant score. Are you with me? 3.434 something. Hello, are you getting it? I'll double click and show you. This row is multiply with this row. This is my A1, A2, $K$, $L2. Hello. This part is K and L cell will have to be locked because the slope is same for all. It's like a regression. B2, C2 is the first record, 0.158 and 0.188 cell. That is the discriminant score for the first record. Then shamelessly copy and drag it here till the end. You get all the discriminant scores. All the discriminant scores. Do you agree with mine? Discriminant scores are obtained. That means, what do the scores tell me? What do they tell me? Yes, scores. Based on this, how the model has predicted, I will have to see. For that, I need a score to cross check. So, one way to do here is, I can find out this formula is here, which we have used for calculating the distance. The mean score for x1 and x2 for the discriminant Z1 represents the discriminant mean score of the centroid, group centroid. A1 x1 bar, A2 x2 bar. Z2 is the score for A1 x1 bar for the group 2. So, I can work out a group 1 score and group 2 score, which I will put with your permission, which is there, Z1, Z2. You agree? Hello? It is there in your presence. Now, what is this score? Can anyone say? Is equal to some product, what is that expression there? A1 into x1 bar plus A2 into x2 bar for the first group. Am I correct? So, what are the means of the first group for x1 bar and x2 bar? Is it written there? A2 into x2 bar for the first group. Am I right? A2 into X2 bar, A1 into X1 bar for the first group, A2 into X2 bar for this, which is available here. This is my A1, A2, am I correct? A1 into this plus A2 into this is equal to some product, ladies and gentlemen, comma, these two means. Group 1. This is the score for the group 1 mean. Correct? Multiply 15.0919 into 0.191, 5.76 into 0.1835, which is my Z1 score. Yes or no? Now, what is my Z2 score? By the same thing, 15 and 5.7 multiply shamelessly with the second group scores. So, it will be equal to some product comma this one. Now, I get two scores here. Is the group 2 score we are getting this or different? 0.05752. Now, how do I assign? A question comes. Supposing my score, one logic is, if my score is closer, for example, the first score, what is the first score? 3.434. It is closer to this or this. So, it is closer to 3.94, therefore, I will assign it as belonging to most admired. Second, 4.35, that is also here. But suddenly minus 0.36, it will be assigned to the second group. In other words, if I compare my score with Z1 and Z2, I can take a call, whichever is closer. In other words, if the score is closer to Z1, classify as group 1. If the score is closer to Z2, classify as group 2. But then what will happen if the score is in between? In other words, you may say that whenever the score is less than Z1, classify as most admired, less than or equal to you can put. Whenever the score is more than Z2, classify as this. Whenever the score is more than 3.94, classify as 1, because this is the mean. This is the mean score of the group centroid. So, whenever the score is more than 3.94, classify this, less than this, classify this, I can do. But then there is a problem. More and less and all, I will get confused. 3.94, 3.43, it is closer. So, one method of doing that is, calculate 3.434 minus 3.94 and do all that. Generate one score in absolute value. Ignore the sign. Calculate the discriminant score minus a second group, absolute value generate. Whichever is minimum will determine the group membership. But the easy way is the famous cutoff point method. If I take a cutoff point, the score, the general rule is that this is one group centroid, this is another. In between also the numbers can come. So, if I use a cutoff point principle, I first take the midpoint of the two as the cutoff point. The cutoff point, I take it here like this, here. Cutoff is equal to 3.94 plus 0.05 divided by 2. Now, if the score is more than 2.0, classify as group 1. If the score is less than or equal to 2.0, classify as group 2. Cutoff point method. First, this cutoff point you asked, I have told you the cutoff point.
But how do we ensure that this cutoff point is also obliging a rule saying that your type 1 and type 2 errors should be equal?
No, type 1 and type 2 is based on the Bayesian probability, Mahalanobis. You'll have to wait. That is classification matrix. Don't get confused with that. Now, don't go to those things. We are talking about scoring. If I take a midpoint, see, let us see here. If I take a midpoint here, the midpoint score is what? Let's understand this. In other words, one logic, let's look at this, please listen, all of you. One logic is, I have two scores now. I am an intelligent person. I do not know cutoff point. So what I will do is, whenever the score is closer to this first group, group 1, it will not be exactly the value, just closer. Whenever the values are closer to the second group, you will do that. That is one approach. Sometimes you could make a couple of errors there, because if there are values between the two, you may have a problem. So what they recommend is, take the midpoint of the two. If the score is more than 2.0181, most admired company. If this, in other words, when I take this as a cutoff point, there are two options. Is it strictly more or equal to? So let me qualify. If the score is less than or equal to 2.00, then it is group 2. More than 2.01, group 1. So any one you take. So all I do here is, ladies and gentlemen, prediction. Shall I put here prediction? Hello? Is equal to if first cell, if, ladies and gentlemen, if the score more than 2.001 and I have to lock it. I am having only one cutoff point. So I have to lock it. Hello. Is it clear? The dollar sign is required because this is a cutoff point score. Then it is 1, else 2. Else 0 poll. If you want, you can put 0, but we have put 2 here. Do you have any objection? You could have put if the score, let me show it here. If the score is more than the cutoff point score 2.0, lock it. F4, then it belongs to 1, else 2, else 0 if you want. You can classify as 0, but here we have put 2. Okay? Hello, is it correct? Else 2. 1. Now drag it here. Simply drag it. No, correct. It will come. Exactly. So now what happens here is 1, 1, 2, 2. There is one mistake somewhere. The computer has made a mistake. Now just see, this is the classification done by the model. Now the accuracy of the classification, type 1, type 2 error, will be based on a confusion matrix or a classification which we did earlier. So in other words, discriminant analysis is a remarkable tool. All the statistical properties you can understand very easily, but it is a scoring model. That's a basic thing. It is based on a score and is extremely useful when you develop a 1000-point scale for credit risk and giving loan in the banks, where even logistic regression cannot match discriminant. Because it is easy for me. If the score is more than 600, give loan. Between 400 and 600, ask additional collateral. Less than 400, reject. Let him be dejected, but I reject. And I have a clear rule. So discriminant analysis, fulcrum strength is, very start it is developed as a scoring model based on a multivariate normal distribution by Fisher. It's not a joke. It's fantastic. Intellectually, it is of a higher order. Fisher has perceived between to within what happens. How do I maximize separation? The clustering type. I have 3 clusters. I have to separate them as much as possible. Tell me a technique where accuracy is perhaps secondary in the sense, if the segments are overlapping and I feel happy that I have got a good classification, when you deal with the new data, it may fail. It's the problem of overfitting. You get the point. So, discriminant is a scoring model. We have got the score, then we have classified based on the cutoff point method. Now, what is the efficacy of the model 24 records? So, let us now prepare here a confusion matrix. Let's say here prediction, and let's say here center, let me put this here somewhere here, prediction G1, G2, group 1, group 2. Now actual, okay, G1, G2, okay. Okay, now is equal to count if. The range, what I need is group 1, I am counting here how many ones are there in group 1. Am I correct? You can even put, if the prediction is actual 0, else 1. You can count that way also. If you count it, how many ones are there? Sorry, comma 1, comma 1, 12. Now is equal to count if by chance any 2 is there. In this case it is not there. We don't have to struggle. Comma 2, 0. Now group 2 similarly is equal to count if, it starts from here, comma 2. Now is equal to count if, comma 1. Now this sum, of course, this is my 12 actual is equal to sum of these rows, very clear, actual. This is 20, huh? Sorry, yeah, you are right, is equal to this, let me put 1 here, you are right, and this should be 2, yeah, correct. Yeah, the crossing, the cross part is equal to this plus this. This is the confusion matrix. The confusion matrix says the overall accuracy of the model prediction actual is 23 by 24. Am I correct? So let me put here overall accuracy. What is the overall accuracy? What is the overall accuracy? Is equal to this cell plus this cell divided by the grand total. 95.83% overall accuracy here. The model has classified. Am I correct? Ladies and gentlemen, do you agree with that? 23 by 24 by formula. Now the question comes, our friend is very fond, the most admired company, how it has correctly predicted. Out of the 12, all the 12 it has correctly predicted. Given actual is equal to 12 companies, the model has correctly predicted all the 12. There is no misclassification. This is the confusion matrix. Therefore, the ability of the model to predict good, most admired, given most admired is 100%. So 0% is the error. Supposing most admired is the reference point, my dear friend. If most admired is the reference point, I will call it as a type 1 error. It depends on the context. Therefore, the errors of misclassification, if I have to do it here, error of misclassification, you might call it as type 1 error, whatever, is equal to 0 divided by 12 is equal to 1 divided by 12. So, there is a 8.3% the computers made a mistake that the least admired 12, the computer correctly predicted 11 out of the 12 correct, but one company after the least admired, the model got confused and placed it as the most admired. It's not so. That's the error. Least admired is 12. The model allowed one of the least admired to be placed in the most admired. So, that is the type 2 error, and type 1 error is 0. The type 1 error and type 2 error are contextual. If you want to predict 0, 1 in a logic model, predicting 1 will be the type 1 error, predicting 0 is a type 2 error. But it's a question of context, and you can look at it in any way you like, it doesn't matter. Send false positive, negative, all those terms they are using, they're unnecessary. It's very easy to. But these are terms that are popular, so in a ROC, if you plot, you may use all of them to impress people. But I am a simple man. I just say there are two kinds of errors. You call it whichever name you have. This is the, in other words, the ability of the computer model to classify most admired as most admired. Hello? Predicting most admired, given most admired. Predicting least admired, given least admired. It has made one mistake here, which is true positive, false positive, negative, all that, which is the type 1 error, type 2 error. That means, what is my sensitivity? My sensitivity is 100%. And sensitivity is the confidence level. 1 minus type 1 error. What is my specificity? 91.8% means about 92%. So 91.67. In other words, 100% confidence level with 92% power, which is the specificity. Specificity is 91%, sensitivity is 100%. Specificity, sensitivity, last time we did, remember, in the logistic regression model, sensitivity is 1 minus type 1 error, specificity is 1 minus type 2 error, meaning what is the power, how much have you predicted as most admired, given most admired, how much have you predicted least admired, given least admired. Classify as least admired, given it is least admired. Classify as most admired, given it is most admired. That's the power of the model. So, which is displayed to you. This is an introduction to Fisher's linear discriminant analysis. This is what Fisher has done. Now, a question will come. Which one is more important? A question will come. Whether EBITDAs or ROTC. Which one is more important? Are you with me? EBITDAs or ROTC? How do you find out? How do you find out? And if you say A1, A2, you may be right, may not be right also. The slopes are influenced by the numbers given there. You do not have a scaling 0 to 1. The scaling problem is there. A better measure will be fill in the blanks. How do you know if a discriminant problem is given to you, you have developed a scoring model, confusion matrix, everything. How do you say, or somebody asks you which variable is more important? Without the slope, huh? Suppose the slope is negative, positive, confusion may be there. Huh? These are all scores. All are scores only. You have forgotten statistics. It's a pity. Now, what you do here is, we have developed this variance of all that expression. So, what you do here is, let's say ROTC. Like, just put here ROTC. Sorry, not this, EBITDAs. First I put here EBITDAs. In this case, both will be closer, but how to find out, I am telling you. ROTC. Now, EBITDAs versus score. ROTC versus Fisher score, discriminant score. What do you do? Choral is equal to choral. So take the discriminant score, EBITDAs, this part, and find out the correlation between the discriminant score and the EBITDAs. Finished. Score. Is equal to, let me say here, EBITDAs, comma, discriminant scores. That is stupid, stupid, stupid. .9963 correlation. The correlation between the discriminant score and EBITDAs is nothing but the correlation between discriminant function and EBITDAs, because discriminant function is evaluated the score. Now we find out the correlation between discriminant score is equal to choral and ROTC. (97, 94). Almost they are very close, and mind you, the ratios are related. The covariance comes there, but what it says is, when you got the magnitude, when you got the slopes here, you got the impression this is very, very important. 15.9, this is 3 times this. No. Correlation when you do between discriminant score and this is 99.6, this is 97.4. The score of 5 has that correlation. In other words, these are the discriminant coefficients. That alone is not enough. The correlation between the discriminant function and this establishes the fact. This is a wonderful measure to know which variable is more important. In some cases, there will be a vast difference. This is called the correlation ratio or the discrete power. Possible, but covariance I have already accounted in the discriminant function. Yeah, that's the beauty. I can't help it. There is a correlation. I have not assumed independent. I have added that. It's possible. Most of the ratios could be, but if there are a lot of variables and there is high correlation, before doing discriminant, I can do a principal component analysis and take the principal component scores for the discriminant and then do that. So how does it matter? This is the one, because it takes this eigenvalue, eigenvector decomposition. So this is, ladies and gentlemen, introduction to discriminant analysis. discriminant analysis as it is by Fisher is what we have done. You get the point? First of all, it is a scoring model. We write an equation Z is equal to the discriminant coefficients with the associated variables. In this case, only two variables. And we need to find out the value of A1 and A2. Therefore, we develop the numerator which is between sum of squares, denominator within sum of square, and the between sum of square achieves the largest distance between the two group centroids and the square. So, we take the distance square instead of the distance. The denominator is within sum of square, the pooled variance of the two, which assumes in the typical t-test, the variances of the two populations are unknown but assumed to be equal. Variance covariance matrix is equal. The same thing. You should all revise those things. Sometimes people do Modigliani-Miller model in financial management, but they do not know the capital debt equity ratio. We have to be strong. So you have to, I'm only saying, remember, it's a great, delightful language. You don't have to tax your mind. It should be a pleasure, like writing a poem on your own. Up, my friends, and quit your books. You don't have to read the book. Become Fisher. You will get it. See the concept. Numerator by denominator should be maximized. How do I maximize x by y? Set the denominator equal to 1. Lagrangian multiplier, calculus. And then find out the value of A1 and A2. Then I work out the discriminant score for all the 24. Then I need to classify. So, I do Z1, which I have written here, is one score. Z2 is another score. And any score which is closer to Z1 will be first group. Closer to Z2 will be second group. But if there is a score in between, I may have a mistake. Therefore, I take the midpoint as the cutoff point. And then if the score is more than this, less than this rule I use, classify, created the confusion matrix and see the overall accuracy, the sensitivity and specificity, and then which variable is important in differentiating the segments or the most admired, the least admired. I said they are very close to each other, but about 99.6% EBITDAs and the ROTC with a close runner about 97%. So it says these two are important variables. If I have to rank it, EBITDA is number 1 and ROTC number 2, which is what we do quantifying the relative importance. But some machine learning, one of the important machine learning today, contemporary. I'm doing a lot of work in the support vector and artificial intelligence. Once I have some more examples, later I can share with you. Support vector missions. That's the modern thing. The kernel algorithm, it uses some geometry and mathematics, and one can learn at a leisure. There's a library and all that. But this is the foundation. So this is discriminant analysis from the voice of Fisher. I am not Fisher. I am representing his philosophy. The voice of Fisher should be heard by all of us, I feel.
So very quickly, let us summarize today's video. In today's video, we understood the concept of discriminant analysis. Then, we understood that discriminant analysis could be used when the dependent variable are categorical and the independent variable are interval scaled or continuous. Moving forward, we understood the main objective is to use the information from the independent variable and archive the clearest possible separation among the groups. We learned Fisher's discriminant analysis and Mahalanobis distance. We learned to apply Fisher's discriminant analysis on data using Microsoft Excel and validate the developed model, that is the accuracy of model using a confusion matrix.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.